牵扯到多少？我大概现在我只看了一下他的说明，然后他就说确实有自己写的，但是呢，还是要做很多。
Okay, so welcome. Today we'll be talking about, first we'll finish up with tasks, and just put up those slides. This is the second part of the lecture today, interaction. And then, depending on how far we get, we will talk a little bit about how we can use multiple views for visualization. But why I'm putting up these slides is because I wanted to talk about some administrative stuff first. I guess you have a couple of questions, and I have a couple of announcements. So, first, about homeworks 2 and 3. I didn't show you yet the histogram for homework 2, so the majority of you did pretty good. So you can see that the two largest bars in this histogram are between like 9 and 10 and 10 and 12. So the average reflects that. We have an average score of 8.88. And in total, altogether, you have used 15 late days, which isn't too much. So we were quite satisfied with homework 2. And yeah, that worked out fine. Homework 3, you submitted it at latest by Sunday night. And usually, like, we try to grade it by Friday and then give you the grades by Monday, but this time the TAs have approached me since they have also a pretty busy week coming ahead with the finals and so on. And they've asked me whether they can grade until, like, right after the finals, so we won't be sending out grades for homework 3 until the first day of fall break or so. So you will not hear about your grade for homework 3 for a while, unfortunately. We thought about, like, the TAs are really, like, and all of them are doing 6 hours of office hours per week, and we felt like this is probably more important going forward with homework 4 than having the grades out on time for you guys. Homework 4. Homework 4 is really more about reading and understanding, and this is really thought, like, we are thinking of this more of a framework for you guys to use when you do your projects. So there you will see there's a lot of text, there's a lot of code, there's very little code that you have to write. So you can basically do the first 3 tasks with probably in total less than 10 lines of code, but you still have to understand what is going on. And ideally you should really understand what is going on and try to understand the details. So we talk a little bit about closures, we talk about event handling, we talk about specific brushes, about scaling, and so on. It's not a lot of work, but it's a lot of reading, but just make sure that you do that. And we also wanted to give you a little bit more time, so instead of the usual Friday deadline, the deadline is on Tuesday night, which doesn't plus the 2 late days, of course, so if you need to, you can submit it by Thursday night and still have a legal submission with, of course, 2 late days. The last part of the homework is a comparison task. So how about I'll just give you a demo of how the homework should actually work. So this is the final implementation. We have the 3 different views which you were provided. So we have the counts of responses, we have the age distribution of the selected set, and then we have the various issues that were reported as being important for the world's development. This is the United Nations data, in case you haven't looked at the data. So what people did is they voted for which issues affect the world, or which issues do they think is most important for the future of the world. So the features that you need to implement, the first one is the brushing here. So you should be able to create this rectangle and drag it around, and you can see how the other charts update according to that. And we will actually talk about the theory behind linking and brushing and about coordinating multiple views in the next lecture on Thursday, but for now I think most of the details, like you have the documentation about the brush API and you have examples online, so this shouldn't be too, well, at least it should be solvable. So the second part here is this transform function. So essentially what we do here is we are using a power scale, and by using the slider we modify the exponent of this power scale, and then we can see like lower variation better if we do that. So again, this is one single line of code. If you know where to put it and how to do it, it's not tough. A bonus, which is a little bit more complicated, is this one here. So that's not really hard. The hard part here is to clip. Like if you want to if you want to like not plot outside here, that is the most difficult part, and combining it with the other brush. So this is a bonus task. I would recommend if you want to do it really when you're done with everything else. It can be tricky, and it's yeah, just make sure that you don't spend too much time on it. And then in the final part of the homework is the comparison. So the idea is that if you have a brush here, you would like given the task that you would like to compare. For example, in April and May, somebody ran a campaign on social media, and you would like to compare the effect of this campaign. So did the audience you target have different issues compared to an audience in a different week of the year? So your goal is that you either like add a second brush here, so that I would have a second brush here on the side, or compare the selected brush to the average, to the global average, and then in this view here, like amend or supplement or modify this view here to allow a comparison between two selections, essentially, so that you could clearly see how frequent is it in one selection, how frequent is in the other selection. There's a lot of liberty you have. It depends a lot on do you have the exact same time frame, do you have to work with proportions, do you need to derive the data, how do you plot your visual encoding, and so on. So you should really think about a couple of alternative designs and then implement your most favorite solution. And you should also submit 2 different designs for that. So, any questions about homework 4? Yes?
So the bottom chart, should that start show up? When should it start to show up?
It should start to show up as soon as you have the task, part 1 finished.
So it should respond to like the brush updates.
The brush updates, yes, but it's like this is really how it should start without a single brush. So in this case, it shows you the distribution of these issues for the whole selection.
So and it said, I think like it says like the event is created in task 4B.
The event is created in.
And that
I
comes
think
through
she's talking
like,
about the update of the priorities with the brush.
Yes. So what's the question?
So I thought it's supposed to like respond to the brush change.
It does. So you can see like if I brush here, you can see how it updates.
Yeah, I guess I'm confused because brush isn't task 4B. Task 4B is the comparative parts, right?
Maybe this is just like a wrong indexing of the tasks.
Okay.
We had a different numbering scheme, so I will take a look at that. So probably it means 3B.
Oh.
Yes?
If you brush some error and then you change the sidebar, what will happen?
This one?
Yeah.
Yeah, so it just works. It's a little, well, this is a bug. I'm still going to show it to you. If I do that, we don't clip. We won't be looking for the solution. Like you don't have to carry it. Clip the brush too. But yeah, this is my thing.
Sorry. So I found on the solution, the GIF picture that you put online, the brush is like in front of the elements, not behind it. If you know what I mean. Like,
Yeah.
Is that supposed to be in front or is it supposed to be behind?
Let's take a look. Looks like it's in front, but it doesn't really matter. It's more about the picking order, I guess, like which one you would be able to click. Because since it looks like it's behind because I'm not able to drag it down here.
Yeah. So is it supposed to be in front of?
Up to you. Maybe the better solution. It depends on what you want to do. If you, for example, it's easier to pick the brush if it's behind. Because I can simply, like down here, if I have a larger bar chart, or if I have higher bars, in this case here, for example, I can't really drag it here. So I have to go up here. But if I were, for example, want to do a hover on any of those bars, conceptually, you don't have to do it, of course, then I still need to be able to clearly select these bars. So the answer is it doesn't really matter. In this case, we've done it behind. You can do it behind or in front, however you like. Any other questions?
When we do our own implementation of a comparison, do we make that a second file?
Depends. So if you if you kind of destroy this view here, yes.
Depends on how wildly different it is.
Yeah.
Okay.
If you really want to remove this or do something completely different, I would suggest you do it in a separate file and just make a note on this page here or link to that. If you don't, you can also put it here to the side. You can rearrange that slightly. That's fine. Anything else? Okay. So the next administrative thing that we should talk about a bit is your project. So it's really time to start thinking about your project. Homework 5, so just like a little bit of information. Homework 5 is your project proposal, and homework 6 is an exercise in volume rendering, and you will be defining, implementing a transfer function widget, implement some basic volume rendering algorithm, and do, as an optional extra credit work, some shading. Homework 5 and homework 6 are going to run in parallel, so that you will have 3 weeks, including fall break, but 2 weeks of classes to do homework 6, but you will also have to do homework 5 at the same time. And homework 5 is really something that you should be thinking about already. It's about your project. So you should, homework 5 is due on October 23rd, and you should really use your fall break to get started. If you have any questions about your project, please use my office hours. Come to see me, talk to me, ask me about the scope, and especially ask me questions about the data. So the critical thing is, what you need is a team. So you have to have at least 2 people, at max 3 people. You have to have an idea of what you want to do, and you have to have a data set that you can actually get. This is the last part, that you can actually get, and where you have a clear plan is important. For example, I've had a team in the past that wanted to extract core rulings from PDFs. I told them, well, you have the PDFs, but this is really tough. People, like, PDFs are simply not easy to parse. And so they said, no, well, we'll be able to do it, and I didn't force them to change the project. So a week before the deadline, they came to me and said they can't do it, and they have to switch to something completely different. The lesson here is really, and this is true not for just projects in this class, but this is true for any kind of data-driven analysis project, you have to have real data. So if you, for example, want to collect Twitter streams over a period of 2 months, you have to get that going now. You won't be able to acquire a huge Twitter data set within one night. So really make sure that you have the data, that you can understand it, that you can read it, and that it's in a format that you can use. That is critical. So ideally, by the time you submit homework 5, you should already have the data on your hard drive. This is really important. So how this will work is we will send out pretty soon, like the instruction for homework 5, and in the instruction for homework 5 you will send us a design document, a plan of how you want to do this project. You will send us a couple of alternative designs that show us that you thought about what you want to do. The minimum requirement for your project is that it's a multiple coordinated view system, so you can't do a single parallel coordinates plot, but you must do like at least 2 different aspects of a data set. And they need to be synced and coordinated. There's an exception. If you have some super fancy, super complicated single view, then we can make an exception. But typically, we would say the minimum requirement is a multiple coordinated view system. The data is completely up to you. So if you're working on a research project with another advisor, just use this data. If you, there's a lot of examples on the website here that points you to possible data sources, from Wolfram Alpha to DataGov to CensusGov and so on. So all of these, these are sources of data where you can download structured data. If you want to do a project in scientific visualization with volumes or flows, that is totally fine with us too, of course. You will be learning more about this starting next week. Aaron is going to give the first lecture on Tuesday, and any visualization task is possible. Yes?
Sorry, I'm just searching.
Oh. Okay. Any other questions about the project?
Are you gonna have office hours the follow break?
Yes. But you can also email me and set up an appointment. Yeah. No, I will be here. So yes. Good. So the last administrative item. Oh, I already mentioned that. scope, and so you should also agree upon with your TA. So you will be assigned like one TA to supervise your project, or me, like we will be splitting this up. And be ambitious. Define your goals and categorize them. And I already mentioned the minimum. So don't do something super boring. Do something that excites us and do something that excites you. And there's also bonus points for your project. So you can save yourself if you didn't do so well in one of the homeworks. Last administrative item is the exam. We will have the exam next Thursday. So generally speaking, everything that I cover until the end of this week is in the scope of the exam, including the mandatory readings. Practically, I won't be asking stupid questions about D3 library functions. So I won't be asking you, what does this particular function in the D3 force layout mean? So if I ask about code, and I would probably ask 2 or 3 questions about JavaScript, D3, and so on, because we have spent 6 lectures on it. If I ask you about code, it's going to be conceptual. So how does D3 data binding work? How do selectors work? And so on. How do you access data? Where is the bound data stored in a DOM? I might give find the bug question. It's not going to be something subtle. It's going to be something, again, influencing the conceptual workings of D3 JavaScript and HTML. There will be a design critique, so we've been doing a lot of those. I will give you an example. You will simply analyze the visualization, list its goods and bads, list what data sources there are, and so on. Please keep it short. I have to read this. Keep it to the point. And then, of course, there will be theory questions. For example, and of course these questions are not going to be in the exam, but what's bad about the rainbow color scale, or what are common spatial data set types? These kind of questions. You will have the full hour. It's probably not going to take you that long. Yeah, so any questions about the exam?
Are we allowed any notes or?
No closed book.
Will we have an example midterm? Like
Nope.
No.
This is the example midterm. Here you have a couple of questions. It's honestly, if you went to class, if you participated here, if you did the homeworks and understood what you did, you won't have to study for it. It's not going to be hard. If you didn't come to this class, if you didn't do the homeworks, if you don't understand what is going on with JavaScript and HTML, you will have to study for it quite a bit. Okay, any other questions? Great, so a lot of administrative things today, but let's get back to some content. Okay, so before we started talking about design guidelines last time, I just wanted to repeat this briefly. We talked about marks and channels, so we had these different types of marks for items and for links. So we had points, lines, areas, or volumes, and then containment connections as marks for links. And then we talked about channels, also known as visual variables, where we discussed of how we can encode the different data attributes. We talked about the characteristics of channels, whether they're selective, associative, quantitative, what their order, whether they can express order, how many of these different symbols we have. And then essentially, like, we went through all of those, and we gave examples like of position, value, color, shape, and so on. So then what we also talked about is Stephen's psychophysical power law. We are pretty good at seeing the difference of length linearly. We're not so good at seeing saturation or area, so we're under or over appreciating those. And the same for brightness. You have to be aware of that when you develop your visualizations. And yeah, the fun artifact is that the electrical shock is highly we perceive it much stronger than it is. And then we did this little example, and it was no surprise that most of you got all of the length examples exactly right. So this is 2 times as long, this is 4 times as long, and then we had a little bit more of a discussion of how much steeper this one is, how much larger this by area is, how much larger by area, how much larger by diameter, and so on. So this was about Marxian channels. Then we briefly mentioned other things that affect accuracy. And here it's important to know that alignment is critical, that distractors are important, that the distance between two things is important, and of course a common scale helps. So in these examples here, we have unframed, unaligned, framed, unaligned, unframed, aligned, and then it's a difference between like comparing those two bars here to those two bars to those two bars versus those two bars. And then we talked about this ranking of, or these experiments that try to determine the quality of these channels, and there were two major, or one major experiment that was later reproduced using mechanical Turk, and then we have this ranking where we can see the lowest error is actually for bar charts that are in close proximity, and we still have pretty good error rates for these cases T2, where we have two segments of a bar chart, of a stacked bar chart, and T3, but it gets worse as we add more destructors and as we add other shapes like pie charts and so on. So this was one of these ranking tables. So depending on what your data type is, whether it's quantitative, ordinal, or nominal, you should use different channels as your first choice. Of course, you don't always have the choice. And so here is an updated ranking of that. And again, this is essentially what this should tell you is that you have differences between these channels, but don't take this like totally serious in terms of, especially in these lower areas here, this is a little sketchy. Is there a question or? No. Okay, sorry. Okay, and then we started talking about design guidelines. So we talked about the work of Edward Tufte and how he hates PowerPoint. So every time you make a PowerPoint slide, Edward Tufte kills a kitten. But what it really is about is graphical integrity and excellence. So you should really have show like what the data tells you. Show that in the design, and don't show like some superfluous marks or something like that. And he came up with this design principle for data graphics, and we had a couple of fun Fox News examples. For example, here if Bush tax cuts expire, it looks like now we're barely paying any taxes, and as soon as the tax cuts expire, we're paying 5 times as much. What happens here is, of course, that the scale isn't used properly. So in reality, this chart will actually look like this, which is, of course, looks, of course, much less dramatic. And here we had a wrong ordering in terms of time. So this is really just sorting by value, but whenever you have time on an axis, you should use it in order, obviously. Then you should be faithful with your scales. You shouldn't do scale distortions. So here would be the correct chart for that. And then we talked about starting scales at 0. Yes?
Well, I had a question about starting at 0 with the bar chart, and maybe this is about my own integrity. I remember one situation I was working on a project and I wanted to compare like average levels of education. Mm-hmm. And I didn't start at 0, I think I started at 12 on the basis of everyone has to go through high school, very few people actually drop out.
Yeah, so as I mentioned, this is very true if you compare, this is kind of a hard rule if you have real ratio data. So if you have like an absolute 0 value. For education, you could argue that you have a baseline. Sometimes it's tough to show what you want to show because variation is a little subtle if you compare that. But then the recommendation I had was to, instead of plotting the raw values, to plot the differences. So you can actually plot the differences faithfully. But it's not an absolute rule, and some people say you can do that for line charts. I disagree. You have to use the same judgment for line charts as for bar charts. So it's a judgment call. Be obvious about it. If you don't do it, and if you have a good reason, there can certainly be situations. But the rule of thumb is, if you have ratio data where you have a true 0, just start your scale. So then we had this example of global warming. This is also about framing the question. So in this case, it looks like global warming isn't really happening. So what we perceive here is mainly that, oh, the highest year was this one, and it actually looks like it's going down. But if we frame this in a larger context, we can actually see that the average trend is going upwards. So how you select the subset that you show also influences your story quite a bit. And then we talked about the lie factor, which essentially can be calculated by the size of effect shown in the graphic versus the size of the effect in the data. And this is really something that you can do numerically. So in this example here, we have a lie factor of 14.8. What we exactly do here isn't that important, but simply like this is distortive, and you should this should come exactly to 1. So the integrity principles that Tufte essentially coined was show the data variation, not the design variation, and be clear, detailed, and thorough with your labeling, and use the appropriate scales. And then the size of the graphic effect should be directly proportional to the numerical quantities. So this is the lie factor. So these are the basic rules of integrity in graphic design. Then we had fun with pie charts. So here's a pie chart that is really hard to read, but I'm not going to go through this in detail anymore. And this is an example of how hard it can be to judge what is going on in the data set, especially for trends. And then if we look at this, we can see there's a couple of clear trends, which are really hard to perceive in pie charts. Yeah, this is a fun pie chart, another fun pie chart. Okay, so this was essentially, this shouldn't be again, we have it already? Okay. Yeah, so then we started talking about chart chunk. So maximizing data to ink ratio. So we had this example that you could redesign like that. You don't need extraneous visual elements that distract from the message. So in this example, you could simply remove these guiding lines. You could remove the color here. You could remove the frame. You could even go further and remove the y-axis here. But of course, this is something that is a bit debated. So we had the question of this, like, which is better? This figure here on the left shows you diamonds were a girl's best friend. That the value of diamond essentially crashed. So we have here's a graphic by Nigel Holmes, and compared to that, we have a graphic that simply is absolutely reductionist. And the question is, what is the better graphic here? And so Tufte and similar-minded people would strictly argue from this shows the data, it has minimal chart chunks, so therefore this is the better graphic. And then some people came along, or here's another example, and then some people came along, and this is where we stopped last time, and studied the usefulness of junk. So is there actually some value of using these superfluous elements, using humor, using graphical elements in a chart? And this was a hotly debated paper in the community. So here are their findings. So they didn't find a significant difference between the plain and the illustrative charts for interpretation accuracy. So we can perceive them as accurately if we want. There is no significant difference in recall accuracy after a 5-minute gap. So if you only if I ask you about the data, about a chart you've seen 5 minutes later, there's no difference. But they had significantly better recall for these Holmes type chart, so for these illustrated charts, of both the chart topics, so what was it about, and the details, what was the trend, what were the categories, and so on, after a long-term gap. So long-term recall was better for those images. And the participants saw the value messages, so what was the chart about? So you guys probably remember that this was about diamonds. You might not have remembered if I only showed you the line chart. And participants found the Holmes charts more attractive, most enjoyed them, and they were easy and faster to remember according to participants. So should we therefore use all of these elements all the time? And the answer is, I think it depends. What is your mission, who is your audience, what are your tasks, and so on. So of course the pros are memorability, engagement, and persuasion. And the cons are, like, they might lead you to biased analysis, they might be less trustworthy, they might be less interpretable, and they might be less space efficient. So my recommendation is you can do this kind of thing if you're communicating some data to like the general audience, to the public in a newspaper and so on. We have in many design studies, we've seen that there's some graphical effects essentially just to catch people's attentions, to improve people's recalls, to make them interested. If you have like an analyst, a scientist who really wants to understand the data and who is invested like really in the data, you don't need them and you should probably not use them. So that's at least my 2 cents. This is still a hotly debated topic in the Infobis community, and there's follow-up studies to that, and there's counter papers to the original paper and so on, but this is just like the rule of thumbs. Don't do things that really hinder perception. So we talked about 3D a bit, but none of you could tell me what the values of the bars back there are because you simply can't see them. There's occlusion and it's unnecessary. Here you distort, like by using these 3 bar charts, you also distort their actual height. And of course here in this case, this is simply the most interesting chart that I could find about banana exports. Okay, so next we'll be talking about tasks. And a critical, like whenever we do data visualization, we are doing it for a purpose. We're trying to solve a problem of somebody. We're doing a data analysis. We're doing a data analysis system that somebody needs to uses to solve a specific problem. And when you design a visualization, and we have hinted at this like colloquially, so what is the goal of this visualization, or what the tasks does this visualization solve, but now we will talk a little bit more in detail about what are tasks. So the first and the key message here is that there are domain tasks and abstract tasks. Domain tasks are specific questions a scientist might have. And there is an infinite number of these domain tasks. Abstract tasks are tasks that we can like formalize as visualization people. So we can say comparison of 2 quantities is an abstract task. A domain task would be understand the correlation of the gene expression in EGFR for 2 different cell lines. That would be a domain task. The abstract task for that would be compare 2 numerical values. So understanding these domain tasks and breaking them down to abstract tasks is really an important skill. And it's probably the most important skill that you can have as a visualization designer. So ideally, if you talk to somebody and you want to understand a domain problem, then you can come up with a list of abstract tasks, and then you can look up, okay, or think about as soon as you know more visualization techniques or more systems, if you have identified the task and the data combination, somebody probably has had the solution already. So you could maybe just plot this with an existing tool, or at least you can take an example at somebody else's work. You will find an infinite number of domain problems, and for many of those you won't have a solution ready, but if you think about it in abstract terms, it will be much easier to do that. So this is the categorization that is used in this in the book, in the textbook. So we have like the high level or 3 different task types. So we have analyze, search, and query. Analyze is about high level choices, and there we also distinguish consume versus produce. Search is about finding or locating an item. Querying is about asking for characteristics of an item and then finding this item, or for example, by itself or relative to others. So here's an example for a task. I could say, find a good university with a high faculty-student ratio in these like university ranking data sets. So in this website here, I could first identify highly ranked universities, and then in the subset compare universities, and then identify those with a high faculty-student ratio. So I could go here, and I could say, okay, these are the top 10 universities according to this ranking, and this is an overall score. And now up here I can switch to faculty-student ratio. And now I can try to remember whether any of those were in this list here, but in fact, yeah, so we can see here MIT is dropped to number 14. So number, like, depending on what is important to you, you could now essentially say, okay, this is a good university and that also has a high faculty to student ratio. You could also do, like, you could derive a ranking with a high weight for the faculty student ratio. And this would be like a little bit more of an abstract task. And so that's something that you can, for example, do with this particular visualization technique. So what this essentially is supposed to tell you is that not everything, not every task or not every way of solving a task can be achieved with every interface. But for this particular problem, there's another visualization technique that colleagues and I developed, and in this case here, what we are showing is a ranked list of universities, and this is the standard combination of factors. And so here we have academic reputation, here we have employer reputation, here we have faculty-student ratio, citations per faculty, and so on. And this is a stacked bar, so the one with the overall highest bar is actually the highest ranked. But now if I say, I'm interested in a good university, but it has to have a good faculty-student ratio, so that is important to me, I could simply modify the faculty-student ratio. So this allows me to solve this task in a different way. And so I can see that University of Cambridge, for example, does much better in terms of faculty-student ratio than some of its peers. So if we want to do contrast Harvard's reputation scores with MIT's, and contrast, match up, and so on are usually indicators for comparison tasks. So what you need to do is first find Harvard and Yale and then compare the two reputation scores. So what I could do is I could go to this website, I could go to overall scores, and then here is Harvard. Oops, I shouldn't click on it. Here's Harvard, and then down here is Yale. And now, instead of overall scores, we want academic reputation. So we can compare Harvard to Yale. So we can see that both have actually a reputation of 100 of the maximum. So in this case, the comparison task is easy. It gets a little bit more complicated if you have a task like find a combination of weights and parameters where Harvard is better than MIT. So in this case, what we're trying to do here is not analyze existing data, but produce a new data set by deriving from the input parameters. And this is something legitimate in many cases. In this case, maybe it's ethically, well, the idea of this visualization technique was really to make people understand the biases of these rankings that I essentially can manipulate by setting these weights arbitrarily. So let's take a look. Let's try to get Harvard into place number 1, and we can try to do that by increasing employer reputation. Maybe not. Or we can maybe do that by citations per faculty. So if I just tune this far enough, reduce this. It's a tiny difference.
Gotta make it really big.
No, it's not good. That's also not good.
So what you're saying is we should all go to MIT.
If you want to
There
study,
we go. There we go. You did it.
yeah, I did it. So now I have essentially derived the ranking that essentially fits into the picture that I want to paint. But of course, this is not what you should do, but the point here is that derivation sometimes is data derivation, and abstracting data is sometimes a task that you as a visualization designer have to do, but sometimes it could also be the user's choice. So in this case, it's the user's choice, but very often it's your choice. So I'll have a couple of other examples where it's more about the developer's choice. So here is an example of how you could do that. Yeah, so citations per faculty is essentially the difference or what makes the difference. Okay, so let's drill down a little bit into these high-level actions of these analyze actions. So we can distinguish between consuming and producing. So consuming is about discovering. If I don't know anything about the data set, I would simply browse it to find something new in it, or presenting. So we had this distinction quite a bit when we looked at, for example, news outlets versus scientific visualization systems. There is a strong divide between them, and of course they have different implications. And then you could also say enjoy, it could be a separate category if you have casual users. You could also use visualization to produce data, for example, to annotate data, like you do an analysis and you notice something about it and you simply tag it, annotate it, and so on. So you create a record. You could record an analysis, or you could record some highlights in your data set. And of course the most important one here is derive. So we had this derive task just now. You like give them input data, derive some higher level output data from it. And derive is really a crucial design choice. So as soon as you've identified your tasks and your data, you should think about like, how do I have to derive the data? And for example, in your homework 4, the raw data doesn't match exactly the task that we want to fulfill, so we have to do this data wrangling. You have to do this aggregation by day. So this is what derive is about. Here's an example for annotation. We've looked at this specific picture, but in this case here, this is the income equality between male and females, and here we have selected entertainment, education, and law. And this little dot here is highlighted, so women earn typically more than 20% less than men, and somebody thought about this and annotated a little story about it. So male tenured professors who earned their PhDs decades ago out-earn female professors whose numbers have grown more recently. So this could be a seniority effect, is the argument of this point here. This is an example of data derivation. So here we have actually a combination of both raw data and derived data. So box plots plot some statistical quantities of data vectors. And so we plot the median here and the quartiles along the box plot, but we also plot the individual data points. And this was especially funny when I found this picture last February, because it was actually snowing like crazy in Boston, and yeah, you can see that outlier pretty clearly here. Here is a good example of a very similar, like who likes soccer? 4 people, 5 people. If I asked who likes football, it might be different. But well, here is a very simple data set. You have football players, their clubs, their countries, the countries they play for in the national team. So this is a list of national team players, and the continent where their club is. So this looks like a very simple tabular data set, and now you could think about how do you visualize this. And if you think about deriving the data and how you can modify this, you can come up with a couple of very interesting visualization techniques. So this is one that I found particularly interesting. So you can see, and now like we had a table and we kind of made it into a graph in this case. So what they did here is they positioned the countries that played in the World Cup here on the outside, and then they put the clubs here in the middle and mixed it with the players. So you can see the big clubs like Real Madrid, they have players from all over the world. So they have players from Germany, they have players from Croatia, Brazil, Argentina, and Spain, versus Bayern Munich traditionally plays with more German players. So you can see that a large part of the team is actually from Germany. And it's also interesting that almost half of the national team of Germany plays for Bayern Munich. That's why they won 28 championships versus 7 for the second most frequent club. And you can interact with this, but this is just like, and it's fun to play around with obviously, but this is just an example of what you can do if you derive data properly. So in terms of actions, we have this mid-level search and low-level query aspect. So that depends on what does the user know in terms of the target and the location. So if you, for example, know the location and know the target, then it's just a lookup. A simple example would be if I were looking for my lecture slides, I know what I'm looking for and I know where it is. So I would just have to go and look it up. If I don't know the target, but I know the location, so I'm thinking about some specific piece of information I have somewhere in my slides, I know in which folder they are, but I still have to browse that. If I don't know the location, but I know the target, this is a locate operation. So if I, for example, were very confused and don't know where my slides are, I could simply use a search box and then locate them. If the location is unknown and the target is unknown, then it's interesting because then we are in this exploration space. So we try to find something interesting, some pattern or something in the data. And then we have these aspects of how much of the data does matter. Like, is it only a single item? Then we can query and identify it. Do we want to compare multiple items? So do we want to understand, for example, spending in the presidential campaign 2012 versus 2016? Then we have the comparison task. Or do we want to summarize an overall data set? So these are these mid-level search and query actions. So here is an example of compare and derive. This is about Greek recessions versus other recessions. And the interesting thing in this chart is that it doesn't show you years in terms of how they progress through time, but it's normalized to years since the start of the crisis. So you can now easily compare the Great Depression in the United States versus Greece's debt crisis. And you can see the euro area crisis in 2008 was essentially compared to what happened in the Great Depression and what happened in Greece was a minor event. Versus Greece, and I guess it's not looking much better at the moment, in 2008 was still very much at the bottom. But in this example, so here we do the comparison, but here we also derive something. So here it's a change on a year earlier, in this case just for Greece. And so this looks a little bit more encouraging because essentially it's getting better. So here we're still losing money, but at the very end, it's actually improving on that. Unfortunately, the trend turned out to be not sustainable, but it's a good example of data derivation to show something. And this is also the example, like if you don't have zero scales, then you could do something like this. So here, you can always show the change, the difference, and then it's, so here, like for example, this is a non-zero scale. And in this case, it's probably fine. But this is a good supplement to this graph. Okay, so why do we do this? So the kinds of questions we want to ask. So A, we want to understand trends. Is it going up? Is it going down? We want to identify outliers. Is there some item in the data set that is very different from everything else? We want to identify features. So is there, for example, some characteristic pattern that we can associate with something else? In terms of attributes, we could look we could look at the distribution of attributes, or we could look at the extremes. If we have one single attribute, if we have many attributes, we could look at dependencies between them, about correlation between attributes, and at similarity. And in terms of networks, what is very interesting is, of course, the topology, and then finding path is another target. And for spatial data, we could, for example, be interested in identifying shapes. So maybe there is a characteristic shape that is associated with a tumor, or something like that. So here's a good example for trends. How did the overall job market develop since the recession overall? And so we have trends on the one side, and then we also have outliers here. So in this visualization, like you can see, by the color, you can see essentially there is a mix of green and red, and then if you scroll down here, it splits this up. So we can see there's a trend of some of these going up, but others going down. And if we facet them by different markets, So, well, this is I can't really, okay. So these are things like fast food, consulting, and computing and biotech that have been doing well. The medical economy has been doing well, but if we look at real estate jobs, we can see that they haven't been doing well. So here we facet it and we find these outliers and we can combine them with the characteristics of the data set. And so this is actually a pretty good visualization, and you can play with this if you like. There's more details and very nice animations. So yeah, take a look. And then once we have found the tasks, we have to choose how we do that. And this is what the rest, like we now have the basic vocabulary to like what are the marks, the channels and so on. We have talked a little bit about techniques, but not too much. So essentially the bulk of the rest of this lecture will be about how do we do this visual representation. So we can arrange things, we can manipulate them. This is what we will be talking about, for example, in interaction. We can facet them, like what we just did, select or highlight elements based on other attributes. We can reduce them, we can filter, we can aggregate, and we can embed. So much of the rest of the lecture will actually fit into one of those classes. So this concludes the task part of the lecture. Now we would be moving on to interaction, but since I have been talking straight for almost an hour, I think it's time for another design critique. So this time, we will be talking about not a news technique that was published in the news or something like that, but is actually published in a paper by a researcher. This is a technique by Marian Dirk, who is in Berlin. So if you go to this link, and I'll open it up later again, you will get to the document. You will actually need your computers, it's interactive. And this is the link to the tool. It's about, you can switch between different data sets here. There's philosophers, painters, musicians. And then you can click on those. And you can also switch from a similarity map to a timeline view. And those two different views. And yeah, I'll hand out the sheet. I'll put up the links again. Then you have 5 minutes to discuss again, and then we'll discuss it with each other.
Sure. Okay.
certain individuals or groups.
So artistic similarity.
It's really annoying. Firefox is refreshing the page over and over and over.
Yeah, I'm using Firefox too. It's sort of doing that to me, but it's not too bad.
Yeah, it's fine in Chrome. I think it's the connections between individuals and their like how they influence each other and stuff. So like if you look at certain people, they influenced others, so they have an influence arrow going toward it. And then if they were somebody that drew an influence from someone else, they have kind of a vacuum.
The size of the circle is down. Oh, then they supported the.
How could this data be acquired? You'd have to get it through interview and
I think a lot of this is probably derived from interviews or something like, oh, I was really inspired by the work of this person or something. You know, like you're saying with interviews.
you could do it with machine learning. It could be done via machine learning. It would take a lot of work to get it coded properly, but I think you could do it.
Yeah, you can definitely do it automatically, and I think what you probably go over is, like you were saying, like interviews or like books. That
No, I mean, I think you can take their music or their picture, take machine
Oh,
learning
and
actually
compare them together and see if they're similar.
You just have to find the right markers. It's possible. And how is each visit? Circles and paths. Circles are artists. Paths are the influences.
It's kind of interesting if you look at the different types. Like painters, if you look at the painter one, then it's a lot more. The connections are usually fewer connections. If you go to the philosopher and click on somebody, then they're connected all over the place. The big people in philosophy are connected all over the place. Aristotle.
I bet I have an idea as to why that is.
I think it's
Words through time have been communicated more easily or better than images.
Oh, definitely.
So if you took more artists now that didn't influence graph then, you get more
I think
influence
you're
that's
right,
going
because now we have the ability to share pictures easily, whereas before, if I say something to you, it's easy to share that. So it's an interesting thing.
And if you look at musicians too, the musicians stopped in 1900, which is about the same time the phonograph.
And when music.
So if you do this with classical composers, you get a much larger range because symphonies have been playing them for much longer.
That's true.
So the medium is
I think the interaction is really what makes this usable.
yeah, it's just a
Because if you tried to show all the links and connections,
show connections on the
and so it provides you filtering.
Well, but are you filtering or are you? It's more selection than filtering.
Because it's all, you're choosing what to view rather than hiding.
There is a search if you want to do like That's weird. When you put in a name, you just get some dots. You just click on the bubble and see how. How would the timeline move? Yeah. So if I put in Flash.
Okay, so what is the data that we see here? I couldn't hear you.
Oh, I was just saying it like shows how like different artists or philosophers or influenced different people.
Yes, and so could you rephrase that a little bit more formally? So we show relationships.
It's a network.
It's a network, exactly. And we have two different types of two different types of edges, which are
They are influenced by.
influencing or influenced by, yes. What other data is there?
How influential?
How influential they are? Yes, and how is that encoded?
Size.
Exactly.
And how different they are.
Exactly. So how they relate to each other in terms of style. What else?
Use color to distinguish the similarity between each other.
Yes, exactly. So the color is used to distinguish the similarity. But the color is not the only thing that is used here. What else is used to distinguish?
Proximity.
Proximity, exactly. So this is what is called like a multidimensional scaling approach. In this case, we have similar items that are similar to each other. Items that are similar to each other are also in close proximity to each other. What other data is there in this plot?
Actual data
Yes. What do you mean by actual data?
or the description
Yeah. So
in the box.
exactly. So some information about the people, and then we also have time. It's not relevant in this plot, but it's relevant in the other plot. So we mentioned that similarity is encoded by position and by color. How are the other types visually encoded? The links, for example. So what do you think is the input data for this? Like we have essentially understood that this is similarity and so on, but do you think they use a classification of styles, for example? Or how do you think they calculate that the Beatles are relevant?
It would have to be
Seems
through
largely
interview.
subjective, although they may look at like biographies or something.
Yeah.
I think it might have been derived from like biography data and stuff like, hey, this is who we were influenced by. We're really proud of the Beatles, and so we wanted to be like them or something. I don't
Yeah,
know. Maybe
that's essentially, yes. So what I'm trying to say here is that this is is actually completely derived from the topology of the network. So the only real, there's a couple of other things, but the most important data sets are these links. And so if a lot of people, if you have influenced a lot of people, you're considered similar to them according to this algorithm. And if you were influenced by other people, you're according similar to them. And that's why the Beatles are here in the center, because they have been influenced by everyone and they're influencing everyone. Whereas other people are more outliers, like you can see David Bowie here is not very similar. So the same is true for, how do you think they encoded the size of the bubbles?
By the
number of outgoing links, I think.
Yeah, it's exactly the number of outgoing links. So you can see the Beatles are the biggest one here, but if you look here, there's only a couple of outgoing links, and then here there's even fewer outgoing links, and so on. So if you look at the timeline view, so what do you notice?
It's not a uniform scale.
Yes, it's not a uniform scale. Why do you think that is?
We have fewer biographies going backwards.
Exactly. And then we have this interesting area in music between the 60s and the 70s where we have a lot of influential people. But if we, for example, switch from musicians to philosophers, this becomes much more pronounced. So we can see that there is like, essentially like here is 2,000 years. And this is 50 years. So these are completely different scales. And I think they're doing an okay job by showing these lines here. So they kind of tell us clearly what is going on. Yeah?
I missed why it was a non-linear timescale.
Why do you think it is? It isn't. They wanted to essentially evenly space out.
I think the domain is too large if you do it that way.
Okay.
Yeah, so essentially like you would have, over here you would have a lot of white space. So you kind of try to maximize like what you can show in the space you have. If you wanted to have it proportional to the time, you would have to sacrifice a lot of information about these bubbles because you would suddenly have only a fifth of the space or something like that to draw the actual bubbles. So that's why they chose to draw these multiple lines here. So what are the different tasks that those two views address?
I think the timeline address, the influence, sort of, it's clearer to see that they are influenced by people before them and they influence people after them. And the similarity addresses the proximity better.
Yes, so it's more similarity versus time. So you don't really see similarity well here. This is more of like really, it's more about conveying the time. So you mentioned that, let me see whether I can find an example. Oh, well, let's go to musicians, that's easier. So you can see how the axis here separated, the y-axis. Yeah, so the influences are at the bottom and the influencing are in the top. Why are the arcs going back?
Yeah, that doesn't, probably from later interviews or things.
Music over the course of a decade.
Yeah, so the reason is, of course, the points are located at the position the band was formed, or they started recording.
Yeah.
But these people lived for maybe, or produced for maybe 60 years. Like, take the Rolling Stones, they were worked together with the Beatles at the same time, but are still active. So you could see that here is a couple of people that started way before the Beatles, but have been active after the Beatles even. So they also had influence on their contemporaries.
The influencing lines are much more successful in this view and easier to follow, whereas in the proximity view, it's really hard to figure out.
Yes, exactly. So here, because we give dedicated space to the links, they're easier to follow and they have like a clear structure. In the proximity or in the similarity view, they're much more all over the place. So any opinions about this chart? You like it?
Yeah, I think it's very good at doing what it does.
Yeah.
Like it follows its intent well, and it's not like trying to represent data numerically and things, and so it's able to use the more abstract forms.
Exactly, and so maybe for this kind of not really hard data, such a non-hard visualization is a good fit. Like we don't show bars or whatever, so bar charts actually wouldn't be better here.
It also makes you wonder how they derive style and similarity if, you know.
Yeah, so we can actually look at the data. So they have, you can see here are the links, and here, so the color, style, and so on is probably driven by genres. And then we have the links here in addition to that. So this is open source. You can play around with it. This is from, the data is derived from a graph database. I forgot how it's called, but they have a link here somewhere. I'm not sure whether it's still working. This is essentially a Wikipedia that is completely formalized, where you have all these formal relationships between all of these entities. That's where the data is from. Yeah, so my personal opinion is this is a really good visualization for what it does, and I really like it a lot. It's fun to play with. It's a data set that I care about. For me, that's always an example of a really well done visualization that also uses some interesting interaction, some complex methods, and so on. Any last comments?
I was just wondering, is there any way to do this without interaction? I personally thought you can't really do this without interaction because there's so many links.
Yeah. And so you're giving me a good keyword for the next part of the lecture. Interaction is really, if you have too much data that you can show everything at once, you have to use interaction to reveal that. So if you could label here the main players, but if you drew everything at once, all the links, all the names, and so on, it would just be a mess. So it's pointless. So they made a conscious decision to simply show you something, and so everybody, like when you see this picture, you know that this can't be it. So like there's nothing in here. So I really have to click some items, and I'm kind of like led to click some items to explore what is going on here. Okay. So we have 10 more minutes to talk about interaction. We probably won't be finishing it. So like just in terms of the exam, interaction will be part of it. I will be talking about multiple views and focusing context next lecture. So we will go through that, and that is what is on the exam, and everything starting next Tuesday is on the second exam. So this comes back to your question. So why do we want to interact with visualization? Well, first we want to explore data that is big and complex, and especially if it's too big to show everything at once. Or we want to see different facets, different aspects of it. So we have maybe one representation that shows me something like a trend, and we have another representation that shows me the distribution. So it's very common, for example, to show histograms for every vector you have in the data set, just that you get the feel of what is in the data. But then you might use some combination of attributes. You might select a subset of that and then look at the details for that. So this is how you use interaction. But it's not only about dealing with big and complex data, it's also about amplifying cognition. So we understand things if we touch them, and we understand things if we manipulate them. So if you take, for example, a Rubik's Cube, and I don't tell you anything about it, just by taking it into your hands and playing around with it, you will kind of understand what is going on. And the same is true for visualizations. So we can really make people understand things more if they interact. They can understand cause and effect much better if they can interact with it. So there's a classification of types of interaction. And so there is interaction in a single view, so where I simply don't interact across multiple views of a visualization. And there you could talk about change over time. You could talk about navigation, panning, zooming, rotating. We will be talking about semantic zooming, about querying, and about focusing context. And then if you have multiple views, it's about how do you coordinate between those views. So there you have selections, things like details on demand. Then you have linking and brushing, which is what your homework 4 is about. And then we can also adapt representations in multiple views. We probably won't even be covering much of the single view stuff today, but this was actually planned to be in the next lecture. So we will first talk about the strategies for dividing visualizations into multiple views, and then we'll talk about interactions in multiple views. One very simple way to use interaction is to see change over time. For example, if you have temporal data, you add a slider, and then every time you drag the slider, you show the data at the state in a specific time point. So here is an example of, there was actually a project for a visualization class by a single person, how the railroads changed the face of America. So what we see here is the states that made up America in the year 1800, and we see the railroads. And so there is essentially no railroads. We see county and state borders. And then we can start changing the years here, and then we see some extra states join the United States. And here are some more states, and then the railroads start coming in. So we can see those links here are the railroads being built, and we can see that the Midwest here is essentially still empty. But then as the railroads are being built, they actually influence the development of America dramatically. And then you can see that now we have a completed net railroad tracks, and we see all of the states joining the Union. So what we do here is really, we show you a different data set every time we change the slider here. And so this is good and bad. I can actually, in this case, it's probably a good solution because we like there's a narrative. It actually tells you about what is going on and so on. But you also have to be very, very careful to remember what was in the previous step. So in this case, it's always growing. So you can take it for granted and you can focus on, like based on your knowledge, you can focus on the new things. But maybe something is dropping off, maybe something is changing. So this is true for the colors, for example, they're changing. So you kind of have to keep very close, pay very close attention and switch between, like mentally switch between the timescales to compare them. So maybe sometimes it's better to show these differences explicitly instead of using this time slider to interact. Navigation can be, like it's the second very important form of interaction. This is about the three major navigation operations: it's panning, zooming, and rotating. So there's two examples. The classical example is, of course, maps. So here I have searched for the University of Utah, and in the context of the world, it doesn't really help me to get home. So I have to rotate it, and I have to zoom in, and then I am panning and zooming in further, and so on. So this is like essentially, this is panning, and this is zooming. And of course, these operations like pan and zoom and so on, they're especially important if you have spatial data sets. Otherwise, you can modify them differently, but if you have things like volumetric data sets, here is an example of an online WebGL renderer. So like here we see like brain and connectivity in the brain, and then there's actually also multiple view systems. So we have the volume rendering here, and you can see these path lines within the brain, and then we have the three axial, sagittal, and, well, forgot the third one, view here to show you more about this. And you can actually switch to a 2D view here. And now I can rotate, and I can zoom, and I can see the flow in here. But I can also modify, like by interacting, I can modify the slice that I'm looking at here. So this is a data set that you simply could not understand if it were like if you just got a printout. And so the way that doctors did that before they had these kinds of interactive visualizations, they simply looked at multiple slices, and they had to mentally compare the slices, which is still a valid approach. But this kind of gives you the overall picture. So we have this pan, zoom, and rotate. Okay. Let me see. Yeah, so this is the last slide for today. The theory behind this is essentially was established by Furness and Peterson in 1995. So the idea is that you have like a defined viewing window, so your full HD pixels on your screen, and then you move it around to zoom in terms of, like, for example, you can think of this as camera movements. And so here, at the bottom, if you have your viewing window in such a way that the whole picture will fit, you will see the whole overview. But if you go out, you can only see the subset here. And this, then within those, like within this cone here, you can actually pan around. So this is the paper that actually established the theory of this space scale diagrams. And then you don't have to do this in spatial data. So here is an example of, again, a music data set where you can do this in data that is not inherently spatial, but in real spatial data sets. So that concludes the lecture for today. Next time we'll be talking about interaction some more. We'll have a couple of videos, then we'll talk about multiple views and focusing context. So see you guys on Thursday.